Yeah, and yeah, I suppose it will be better to start immediately from the Hamiltonian. And my talk will be about chiral magnets. And this Hamiltonian is the most basic Hamiltonian to describe the physics of magnetic textures in chiral magnets. So actually you can see there is two Hamiltonians here, but this about the same. So if, for example, someone prefer lattice Hamiltonian, it's the first one, and another one, it's for the people who prefer continuum approach. But even if you prefer continuum approach, if you will try to solve the bottom Hamiltonian numerically, you have to implement some, for example, find a different scheme, and up to second order, this scheme will be exactly the top Hamiltonian. So these both Hamiltonians about the same. Yeah, and what kind of interactions we have? We have a exchange, ferromagnetic exchange, Dzielaszynski-Mori interaction, it's in the middle, or for continuum representation, it's also named Lifshitz invariance, and Zeeman energy, so the energy in external magnetic field. Yeah, and the very important thing that I will talk about classical approach. So the spins, it's just the arrows with fixed length, with unit length. Yeah, and yeah, so we have a lattice of such a spin, and there's a very big amount of spin. So this is a very reasonable approach to investigate such kind of phenomena. Yeah, and how we will try to solve this Hamiltonian. It is a very complicated nonlinear problem. Yeah, and one of the better way it's use, of course, numerical techniques. Yeah, and this is a very simple scheme from my point of view. What is the state of the art numerical tool? And there is a four very important components. The first one and the main important, of course, it's advanced algorithms. Because if we want to solve a very big system with a very big amount degrees of freedom, we have to implement very optimal algorithms. And yeah, the example is here. It's there is a we use nonlinear conjugate gradient method with so-called Atlas subroutine to keep this nonlinear constraint that modulus of the vector is fixed, because it's in the traditional approach, in the traditional solutions to the problem of minimization, there is a big difference for the problem with constraint and without constraint, and such nonlinear constraint is it's a very big problem, and we can solve this problem in most optimal way. The second one is the usage of fastest available hardware, and today such hardware, it's a GPU, so graphical processor units, and they clusters, of course, because of so-called massive parallelism. So we can run 100,000 threads in parallel, and they can share the memory, and the memory access also very fast, and so on. So this is one of the most effective hardware for today. Another very important component, it's a live graphical interface. So it is also very important because it is much better to have the picture what is happening in your system immediately during the calculation, not to plot some dependencies after, but right now, because you can see that if something goes wrong in something goes that you did not expect it, you can stop, you can interrupt, and so on. And it is very related with the last one component, it's interactivity. So we have to be able to go inside these simulations and to change something in real time. So by other words, we can do something like real-time experiments using some, not only keyboard, for example, but more sophisticated manipulators like mouse, or even more sophisticated. So that was actually a short introduction. And now let me to move towards these live simulations. Yeah, and I will use my laptop equipped with a modern GPU. Yeah, and we'll try to show in real time this physics and the particle-like states in chiral magnets. So let's start with the simplest case, with two-dimensional case. So we have a monolayer in external magnetic field. And let me to create the skyrmion. Yeah. So this is a common chiral skyrmion, or vortex, if you wish. Yeah. So what we can do? We can investigate it a little bit. So first of all, the skyrmion is a particle-like state. Why it is particle-like state? Because it's indeed like particle, so it can move. If we will try to distort it, it will try to preserve the shape. And we can create another one, and they can interact like particles. So it's kind of scattering, right? So yeah, indeed, it's like particle. Yeah, but of course, it is only in the certain range of parameters and so on. So for example, I can reduce the external magnetic field. Yeah, and what is this? Is elliptic instability. So everything is spreaded. Okay, what else? Let me to create a bigger amount of skyrmions. Yeah, and increase the magnetic field again. Yeah. So, and what we can see a rearrangement of these skyrmions into a lattice. And because the skyrmions is circular-like shape, yeah, they prefer to arrange into triangular lattice, of course. So let's do some distortion. Yeah, yeah, and they try to rearrange again in triangular lattice, but with bigger distances, right? Okay. So let me to switch in such. Yeah, they interact and rearrange. Yeah. So, but you can see in this picture that all the skyrmions is the same. So it's like twins. Yeah. And the question is, why skyrmions? Why this is the skyrmions? Because decades ago, so 10 years, 20 years, 30 years ago, this particle-like states was known as magnetic vortices, if you prefer chiral magnetic vortices. So the skyrm idea was sufficiently wider than the existence of one particle-like state, because the skyrm idea was nonlinear field theory. Nonlinear field theory. And in this theory, there is different particles with different masses or energies, and the difference is related with topological charge. So, and these particles in skyrm model was atomic nucleus. Atomic nucleus, and this topological charge was a baryon number. So, but what we have here? We have here only one. Yeah, only one skyrmion. There is no more massive particles, antiparticles. So only one skyrmion. So yeah, let's investigate it in more details. Yeah. So let me to clean. So, and to put in the pose, and now I will create the following. Two textures. These textures not yet optimized, it's just initial guess. So on the left side, it's something as it was, so chiral skyrmion. And on the right side, yeah, look, it is another kind of another vortex. And if you will calculate the topological charge will be opposite to the left one. So from certain point of view, this is an anti-skyrmion. Yeah, but there is a difference if you will consider this guy. Image you moving in any direction in the plane, and you can find that along this direction, the spin rotates in only one direction. So only in certain chirality. Chirality preserved, because chirality, which is responsible for stabilization here, have concrete sign, and chirality is fixed. But for this guy, chirality is not preserved. There's two kinds of chirality. Okay, but anyway, we can try, right? So this is the initial guess. And now I will start the minimization and look. So, yeah, let me to check the external the external magnetic field. Right, it's correct. So, yeah, let's start the minimization. What will happen? Yeah, something sufficiently happened with the right one. Yeah, and now if we will consider, we will find that after minimization, it became again the same. So it's exactly the same skyrmion as this one. So let me switch to top view. So it's exactly the same. So the presence of different chirality, it's very, very unfavorable for the system. And the system transformed this skyrmion through the singularities to common skyrmion. So we tried to create anti-skyrmion, but without success. But let me to destroy these guys and create again. Yeah, there is a very important remark I have to add here. So yeah, I have to add here that the chirality here for this calculation, it was chosen certain certain set of Lifshitz invariant, which is related with certain kind of structural symmetry of the crystal. For another kind of crystals, it may happen that such kind of skyrmion, which here is an anti-skyrmion, it's most favorable, so it's a stable skyrmion. But another skyrmion, this one, become unstable and so on. This is because of very interesting, remarkable property of the systems with different Lifshitz invariants, because between this system exists a certain kind of isomorphism. But for such a system, such a guy is stable. The situation is absolutely the same up to inversion. So that means we know that such texture is stable, but antiparticle to this one is unknown and so on. And we didn't know about the existence of more heavy particles and so on. So, okay, let's. lattice, of course it's fixed, just like atoms. Yeah. Of the lattice. Yeah. The position of the spin is fixed, of course. Yeah. We are talking only about the magnetic structure which lived on the sides. Yeah. Just the simplest case. So, but yeah. Actually, recently we solved this problem and found how overcame this protection of chirality for the existence of antiparticles and more heavy particles. And the recipe is the following. So, look. Yeah. So, this guy on the right, if you will calculate its topological charge, it will be opposite to this guy. So it's very interesting that the presence of chiral interaction sufficiently change the morphology of antiparticles. And yeah, so it's very interesting. So this is a kind of anti-skyrmion. It's stable. So let me try to perturbate it. Yeah, look, it's stable. It's also particle-like. It can interact with common skyrmion. And the feature is very interesting that particle and antiparticle repel each other. Yeah, and another interesting feature is, another interesting question is about more heavy particles. So the skyrmion with high topological charges. And the recipe is the following. So let me try to do that. So we can create a 2π domain wall and put inside skyrmions. That's how. And this guy on the left, it's a naturally charged 2 skyrmion. Oops, I destroyed it. Yeah. Yeah, it's stable unto the certain amplitude of perturbation, of course. And if I will do the following, it will be skyrmion with a topological charge 3 or -3, depending on the which kind of agreement you have for the choice of sign of topological charge. So, and they also repel each other. So, this is very so we discovered and published this very, very recently, and this is a solution, and now we can really tell that this is indeed skyrmions, because the skyrm mechanism of generation of more massive particles and antiparticles now is discovered. Yeah, and the problem was, the solution was unknown before because of such very, very sophisticated morphology. So it's not obvious, right, that more heavy particles lose their axial symmetry and have so sophisticated shapes and so on. Okay, now let's go to maybe less interesting case, but more realistic in many experiments. Let's go to 3-dimensional case. So now we have a plate and bulk type Zelashinsky-Mori interaction. So in this system, the ground state, actually it is not ferromagnetic one, but we can introduce second plane and investigate what happened through the thickness. And in certain diapason of magnetic field, the ground state is a cone state. So it's non-homogeneous state. And several years ago, for many theoreticians, was not obvious that such kind of state is allowed the presence of skyrmions inside. Yeah, but we showed that it is possible. Yeah, let me to show the skyrmion inside. Oops. Yeah. Yeah, but of course this skyrmion now is three-dimensional, and it is not just a circle, but tube, skyrmion tube. And yeah, the small remark how we draw this tube. We draw, for simplicity, only such a magnetic arrows which is in plane. So, by other words, the magnetic arrows which belongs to the equator of the space of order parameter. So, this circle. Yeah, and this is a very nice way to show the internal structure. So, such kind of tube. Yeah, and it is very interesting that another group of theoreticians, after we showed that skyrmions indeed exist in cone phase, they found an interesting feature that in cone phase, the skyrmions not repel each other anymore, but attract each other. So look. So, attraction instead of repulsion. So, and this is very interesting and could be investigated in experiment. And yeah, so from certain point of view, the cone phase and the skyrmions inside the cone phase works like a kind of glue, which help to skyrmions to be closer, so a long-range attraction. But there is a even more interesting phenomena in 3D. And this phenomena is this guy. So, this is a specific kind of soliton which was unknown before, and now we call it chiral bobber. And what is this? So, it is very interesting because this object it's full of topology, but if we will combine all this topology together, it has no topological charge. So let me to explain. So first of all, you can cross this structure by the plane. For example, you can consider the top plane, and at the top plane, this structure will be like skyrmion. So we can calculate, for example, the topological charge in plane, and it will be -1 or +1, depending on the choice of signature for topological charge. Yeah, okay, but if we will go deep inside, especially if we go deeper than specific point of this structure, this topological charge disappear, will be 0. Yeah, but at the same time, we can calculate absolutely another kind of topological charge, and because of this point at the bottom. So at the bottom of the structure, there is so-called Bloch point, which is also known in magnetism as hedgehog, magnetic hedgehog, and also known as magnetic singularity and emergent Dirac monopole. It's all about the same. Yeah, and we can calculate another topological charge for this structure, and it is also non-zero. It is also non-zero, so two topological charges we can calculate. But if we will combine all together, and from the point of view of homotopy principles, this guy have no topological charge and has no topological protection, because it's very easy to imagine that this singular point, which is on the bottom of this structure, can just escape through the surface. Yeah, just go at the surface and all the structure disappear. So it's not protected topologically, but it's stable. So that's important. Okay, and another short example. Now we will go to even more realistic simulation. And so here the parameters chosen for real material for a film of iron germanium with approximately 100 nanometer thickness. And in this calculation, we will include also dipole-dipole interactions. So by other words, the stray fields or demagnetization fields to be so realistic as possible. So let me to create the skyrmion and also the chiral bobber. So I will try. Okay, so we have skyrmion and chiral bobber. And right now, the dipole-dipole interaction is switched off. So the calculation exactly as was before, without dipole-dipole interaction. And what I will do now, I slightly increase the power of dipole-dipole interaction from 0 to realistic one. Yeah, and you will immediately observe what will happen with the structure. So, okay, 10%, 20, 50, 70, 100%. So now the program minimizes the system with realistic dipole-dipole interactions. And what we can see here. So from first point of view, it's something spreaded. It's everything as it was is disappear. But no, actually no. Let me to increase the magnetic field, the external magnetic field. Yeah, and yeah, let's consider this texture. So approximately it's the same skyrmion tube and chiral bobber. Yeah, a little bit distorted. For example, the chiral bobber become more convex. More convex, yeah, they exist. Okay, and now I will do the following. I will go back. So I will decrease the magnetic field. And switch off the dipole-dipole interaction. Yeah, so exactly at the beginning. And what I will do now, I will decrease the magnetic field only. So the dipole-dipole interaction is absent. Yeah, and the behavior approximately as it was, then I increase the dipole-dipole interaction. The structure spreaded. What does it mean? That the using of simplified Hamiltonian without dipole-dipole interaction, it's of course it's some simplification of the system, but it is very, very good approach, because what actually dipole-dipole interaction do in the system, for example, in the film, it's just change. So it's like a prefactor on your external magnetic field. Yeah, and the influence on the shape, of course, it persists, but not very, very sufficient. Yeah, and yeah, at the end, let me to draw your attention to our last works. So the first one, it is about this diversity of skyrmions in chiral systems. Yeah, if you're interested, you can find more details. So the second one, it's a paper with a huge contribution from experimentalists, where we found chiral bobbers in experiments. So the chiral bobbers, not anymore a theoretical particle-like state. It's a real, and it was detected and measured very carefully. So, and the last one paper, of course, also with huge contribution from experimentalists, In this paper, it was measured this remarkable interaction between skyrmion tubes, and on the quantitative level, it was compared with numerical calculation and was estimated with beautiful behavior that being in the cone phase, the skyrmions attract each other. But if we will increase the external magnetic field so much, then the tilting angle of cone phase becomes 0, so the cone phase transformed to saturated ferromagnetic state. The theory become like two-dimensional, and skyrmion become repel each other. So it was demonstrated, measured. So this is you can find more information in the last work. So that's all. Thank you.